Hi, my name is Evan Chang-Siu, and this is our first lecture in ET250 circuits. And today, what we are going to cover is the difference between physical quantities and units. And then we're going to talk about these four physical quantities: charge, current, resistance, and voltage. These are the symbols, these are the units. And then we're going to tie it all together with this very, very important law, Ohm's law of V equals plus or minus, and that plus or minus is very important, plus or minus IR, which is current and resistance. So voltage equals plus or minus current times resistance. Okay. So the way I'm going to hold these lectures is I'm going to basically explain my notes. So I have all my notes explained here, and I'm going to go over them. And then for things that like numerical examples, I'll actually write them out and take a little more time. And then when we meet over Zoom, I'll review the notes again and answer any questions that you guys might have. So I hope you guys enjoy, and yeah, let's continue. Okay, so again, physical quantities versus units. Let's start with this. And the first thing we want to look at is, well, what's a physical quantity? And you guys should already know this, but let's just look at the definition. So it's a physical property of a phenomenon, body, or substrate that can be measured. And so this is the key point. It can be measured, right? And so some examples are length, time, mass, weight, something like that, right? If you can't measure it, it becomes difficult, right? And so it doesn't fall into this definition, right? Now, a unit is going to be the standard of measurement for that physical quantity, right? So it's a subtle difference, and we sometimes interchange the two, but I do want to make sure that we have the distinction in our mind. There's a difference between the unit and the physical quantity, right? And so, for example, if you have length, then the unit could be feet, meters, inches, centimeters, right? Something like this, right? So here's a physical quantity on the top, and here's a unit, feet, meters, something like that. If it's time, you have many units. You could have seconds, hours, minutes, right? And then if you have something like mass, you can have something like kilograms or even slugs, right? That's another unit for mass. And weight, you might have newtons or pounds. Okay. So these are just an example of the difference between physical quantities and units. I know very, very basic, but I do want to make sure that you guys have that understanding. Okay, so there's four things that I want you to remember when you're looking at the distinction. And these four are, well, what is the physical quantity itself? Okay. But then what is the symbol for the physical quantity? What's the unit and what's the symbol for the unit? So there's really four things you have to memorize, and they get kind of confusing. Unfortunately, as an engineer, you just got to deal with it and memorize, right? Okay, let's do an easy one. So an easy one, a physical quantity that's relevant to this class is voltage. So you have physical quantity voltage. What is the unit, or sorry, symbol for this physical quantity? The symbol is just V. And sometimes we actually use E for electromotive force, so don't get confused with that. The unit is a volt, so it's actually the same name as the physical quantity, the unit and the physical quantity. And the symbol for the unit is also V. And what I like to do, you don't have to do this, but I like to do this. I put a bracket around the symbol for the units to delineate the difference between this and the symbol, right? Does that make sense? Or for the physical quantity. So that way I can tell them apart, right? So I try to do this everywhere I go when I'm writing this. Again, something you don't have to do, but it helps me. Okay, let's do a more difficult one. Okay, so a more difficult one might be inductance. Okay, and we'll see this later on in the middle of the class, inductance. Again, you should have seen inductance in physics, but the symbol for for inductance is not I, it's L. We've already used I for current, as you'll see later, right? The symbol is L. And then the unit is actually a Henry, right? So notice all the differences, I, L, H, where this is V, 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 right? So a little more difficult. And the symbol, well, the symbol at least matches the Henry's H, right? And again, I put hard brackets just to delineate, okay? So again, four things to remember: physical quantity, symbol for the physical quantity, unit, and the symbol for the unit, okay? Not too bad. All right, let's keep going. Um, some added confusion, right? Some added confusion is that multiple units for the same physical quantity, right? There are multiple units. So you saw that here with distance or length, you had meters and inches, right? And you have to know that this can be the case, right? It's just different standards, right, of measurement, right? Um, Here's some fundamental examples. Here's energy, right? Energy, physical quantity, and we have many units. We have, I don't know if you knew this, but a joule and a Newton meter are actually the same. They're equivalent, right? A Newton meter we think of as torque, right? But it's actually equivalent in units to energy, which is joules. You also have a BTU, British Thermal Unit. This is also a unit of energy. Okay, now they're not equivalent to a joule or Newton meter, but it's another unit of energy. Okay, power. Power is the derivative of energy. This is a very, very important concept, right? And we use watts. And notice we have joules per second, Newton meters per second. All these three are equivalent, okay? Another way that we describe power or measure power with our standard measure is horsepower, okay? Length, we already talked about length, meters, centimeters, millimeters, feet, inches, miles, right? Imperial and SI systems, okay? So fundamental stuff, things you should know, of course, but I'm just really highlighting it because as we add more physical quantities, I want to make sure you're memorizing all four of these things, all right? Okay, let's dive into some of the fundamental units of electricity, okay? And the first one is going to be charge, all right? And we talked about on that on the outline. So we got physical quantity charge. We have the symbol, which is Q, not C, it's Q. The unit is a coulomb, okay? And the symbol is C. Okay, so let's kind of talk about charge. Well, we already know that like charges repel and opposites attract. And so if you had a positive and positive or a negative and negative, they don't like to be next to each other, right? But if you have a positive negative, they are attracted to each other, no problem, right? Again, basic stuff from physics, right? And what I like to do is for these physical quantities relating to electricity, I like to bring up a hydro analogy, and so that we relate it to water. The analogy isn't perfect, but I hope it helps give you some intuition. So I want you to think of charge as just the physical medium of water itself. So my hydraulic analogy is that charge equals just water. All right, it's the medium at which that can flow, that can have pressure, so on and so forth. Okay. All right, let's keep moving on forward. So some common values for charge, some common values. Well, we have our friend the electron, right? Very small amount of charge and it's negatively charged. Negative 1.602 times 10 to the minus 19 coulombs. Good. Coulombs, right? A proton is the positive version and it's the same amount of charge, but it's a positive value. And again, the 10 to the minus 19 scientific notation, very small, okay? According to Wikipedia, kind of counterintuitive, a double A battery has 5,000 coulombs or 5 kilocoulombs, whereas a lightning bolt will only have 15 coulombs, right? Kind of weird that this double A battery has so much more charge than a lightning bolt. Okay, now up to 350 coulombs is possible, but still smaller. Weird, right? But because you can have a lot of current and voltage, right? And in a very short amount of time, you have a lot of power, right? You have a lot of energy transfer. So even though the charge might be not a lot, you can have still a lot of power. Right? Okay, let's keep moving forward. All right, another physical quantity closely related to charge is current. All right, so let's look at current. So current, we use the symbol I. All right, so we have current I, and the unit is amps, and the symbol is capital A. Again, these are one of like inductance where it's like you got all the different, starting letters. All right, so current I, ampere A. All right, now the relationship between an ampere and a coulomb is that an ampere is a coulomb per second. Just like in physics and dynamics, a velocity is what is the unit? Meters per second. And distance, we have meters. And so you have meters per second for velocity, and you'd have meters for distance. So velocity is the derivative of distance, right? So same with here. you have an ampere, which is essentially the derivative of charge, right? The time derivative. Okay. And then I have that here. Current is charge per time. All right. And the way we're going to define it in this class is current is the flow of positive charge, right? And like I said before, I want you to think of a rate or derivative, just like velocity is meter per second, current is coulombs per second. The other key part is direction matters. So you need an arrow. You must have an arrow when we're dealing with these circuits, right? It tells you, well, what the sign is, right? Okay, so here's an example. You have some circuit element, right? This could be a resistor, inductor, capacitor, voltage source. And let's say I tell you that the current is some number, I. But it would also be very important to tell you which direction is the current flowing. Is it flowing down or is it flowing up? And what we say, I had a professor that would say this on the street. as we say, mathematicians or physicists or engineers on the street, we say current through a circuit element, not current across. We'll reserve across for voltage, right? Okay. Now, so for example, here you can see we have an element, and let's say we have 3 amps going down. This is equivalent as the same element with the arrow pointed up, but a negative number, right? We kind of have a double negative going on, right? So these are exactly the same thing going on. 3 amps going down or negative 3 amps going up. Okay, this is a big point of confusion for new circuit students. So make sure you get this straight, right? Get this all figured out. Okay, let's go to the next one. So the next thing that I want to highlight is that there are some conventions for not just the arrow, but also these little letters. So what you might see is you might see something like IAB, right? Well, what is AB? Well, AB, they correspond to these two nodes. And what you want to know is that AB assumes that the arrow is starting at the first letter and going to the second letter, right? Okay. So IBA would mean that the arrow is pointed from B to A, right? So you always start the first letter and go to the second letter, right? And so what you might see in a homework problem is this without the arrow, IBA like this, and you would have to know to put the arrow from B to A. Vice versa, if you had the arrow and they asked you, well, what is the two little subscripts here? You could say, well, the node here is B and the node here, so this must be IBA, whereas this arrow corresponds to AB. Not a big deal. Or I shouldn't say not a big deal. It is a big deal if you get it wrong. It's not tricky to understand. Okay. The hydro analogy for current is the flow of water. So charge is water itself, current would be the flow of water. So imagine a pipe, the current is how it flows, okay? All right. Another important point is, as I said before, the arrow shows the flow of positive charge, okay? Now, that is opposite of electron flow, all right? So if I see an arrow in our examples, it would be equivalent to an arrow in the opposite direction for the electrons, right? And a lot of vocational textbooks will actually have the electron flow as opposed to the positive charge flow. I know it's a point of confusion, but I just want you to make sure that you're aware of these things, okay? Here's an interesting example, a practical example of where this is important. Let's say you have a welding machine, and I know Cal Maritime students, at least the ones sampled in the past 7 years that I've taught, have experience with welding, or a lot of them, right? And so here's an example of a welding machine. You usually have a plus or minus terminal, right? Okay, so if any of you have done TIG. And then you have a table here, and then you'll have your electrode with your tungsten, and then you have your grounding clamp. But notice how we attach the grounding clamp to the positive terminal, right? Kind of weird. And the electrode we attach to the negative terminal. Again, kind of weird, right? Why don't we attach the grounding terminal? Well, the reason why is because electrons are going to leave the negative terminal, right? Now, conventional current is going to go this way, whereas electron flow is going the opposite. That makes sense. So let's follow the positive convention like this, right? Convention, positive convention means the current is leaving the positive terminal, but electron flow means it's leaving the negative terminal, like so, right? Opposite, no problem. But the reason why we do this is because you want the electrons to flow off the tip of the tungsten onto the part, the table, or whatever you're welding. Interesting thing I learned when I took a welding class, right? But that is the subtle but important difference of electron flow versus what we will use in our class, positive charge flow. Right? Okay, some common values that I want you to be aware of, right? And this is for safety. There is the let go current. This is only 10 milliamps, 0.01 amps, right? M for milli, just like K for kilo, right? The amount of current that won't let you go or let you let go, right? So if you are holding something and you somehow have 10 milliamps of current flowing through your hand, you will not be able to let go. That could be a problem, right? Because now you're stuck to something that could be either hot or just very dangerous. And why? Well, our muscles respond to electrical signals. And so when you have a 10 milliamps or more of electrical signal riding through your hands, it's overriding the electrical signal from your brain going to your muscles. Well, you don't get to command that muscle anymore, right? Okay, lethal. Doesn't take much. 100 to 200 milliamps. That's 0.1 to 0.2 amps. That will kill you, especially if that goes through your heart, right? No bueno. Okay. Now, a toaster can deliver 20 amps. Whew. Yep, that could definitely kill you. And a Tesla Model S, yeah, this thing can put out 1,300 amps, 1,300 amps, and I think the later versions can put out even more, right? The reason why these toasters and stuff don't kill you right away when you touch them is because there's a high resistance, right? They make sure that the casing is protected and insulated, and also just your hands itself, your skin usually has enough of resistance on your skin, but if you have a cut or moisture, enough, if you get enough current that goes through, game over. Not good. Okay, let's follow it up with resistance. So we went charge, we did current, and now we're at resistance. We'll do voltage and the Ohm's law, right? Okay, so let's look at resistance. So the physical quantity, again, the four things: resistance, R, ohms, and the symbol is this omega, right? This Greek letter omega for ohms or resistance, right? And the symbol or the circuit symbol is this kind of jagged line here, all right? Okay, the hydro analogy that I like is a rough pipe. Okay, so imagine you're trying to get current to flow through here. Well, these little jaggies in the rough pipe are going to slow it down. They're going to slow down the current, right? And here's one of our equations that I want you to, again, remember. We're going to have two equations of resistance. One is going to be Ohm's law, and then one is this resistance equation. Okay, so this resistance equation, I think, is best highlighted with an example. So let's look at this situation. Well, we have a wire here. We have some length of wire, and so we have some cross-sectional area. And so before we even look at the equations, let's try to imagine what is going to affect the resistance, right? Well, the material itself will probably affect the resistance. If we use wood, we'll probably have a high resistance. If we use ceramic, high resistance. If we have copper, low resistance, right? So the material is going to be important. Good. Probably if it's longer, we're going to get a higher resistance, right? Because we just have more pipe to go through. And then for the cross-sectional area, if we have a bigger cross-sectional area, we're going to have probably less resistance because we have more surface area to travel through, right? It just makes it easier, right? So you could sum that up in this equation here. R equals rho L over A. And let's parse this out. Rho is the material constant. So if it's like I said, a ceramic, this is going to be a large number, right? This rho. L is the length. Yep. So if L gets bigger, R gets bigger. Good. It's in the top, the numerator, the upstairs. And A is in the downstairs, the denominator, which means if A gets bigger, the cross-sectional area gets bigger, then R is actually going to get smaller. They're inversely proportional. Okay. And so rho is the resistivity. It changes with material. And we can figure out what the units are pretty easily, right? I'm not going to do it yet, or sorry, show you, but let's try to figure out again. If we have rho here, and we know that this is let's say a meter, and this is a meter squared because this is area. then R is ohms, so it's an ohm meter squared per meter if I bring these to the other side. So you're left with an ohm meter, right? Because this one of these meters canceled out. Okay, and again, copper, aluminum, they're gonna have low resistivity. These are the ways I want you to start thinking about equations when you see them, not to just blindly accept the equation, but to parse through and go, what does that equation mean? What's the intuition behind that equation, right? If you constantly practice that, like what is the intuition, you're just going to be a better engineer, and you're just going to have a better understanding and more intuition. And I'm going to really preach this intuition. I want you to build this intuition constantly throughout our time together. Okay, let's keep going. So resistance, we have our nice equation, R equals rho L over A. Okay, and so again, we can decrease resistance by decreasing the length, right? Shorter wire, less resistance. We can choose a material with less resistivity. We can increase the cross-sectional area, right? These are the ways to decrease resistance, right? And here's just a visual, right? This is going to have more resistance because I made it longer and skinnier, right? This is going to have less resistance because I made it shorter and fatter, right? So just to visually hit home this equation, all right? So if you're in the field and you see these wires that are thick, right? You can imagine they're thick because they wanted the resistance low so that they can allow more current through them. If you see little signal wires for like a microprocessor, you might see little wires, right? Because they're just carrying a little bit of current and they're just sending information back and forth. Okay. All right, let's keep moving along. Okay, so some common numbers. 9.71 times 10 to the minus 8 for iron for its resistivity in ohm meters, right? And then these are a few more values, right? And notice I've written it out as more conductive. So let's compare. So you have iron, aluminum, gold, copper, and silver. So 92211, right? What's interesting is you'll see here copper is down here at more conductive, and aluminum is actually less conductive. Yet we see a lot of electrical wires using aluminum, right? Why not copper? It seems like copper is more conductive. Well, there's other properties beyond just the electrical performance, right? And so you might choose aluminum because maybe it's stronger. Maybe you can actually build a lighter structure, right? Or more reliable structure, even though you get less electrical performance, right? Same with gold, right? You wouldn't build maybe your power transmission system out of gold. It's just so expensive. So there's a lot of factors that come into play as an engineer, not just the pure performance. When you might go, oh, okay, I want to pick silver, right? I want to pick gold over iron or aluminum, something like that. Okay. All right. Let's. Here's an example. What is the material of a wire? So maybe we can do this example. I'll write this example out. So I'm going to pull this to the side. So let's say we have R equals 0.0359 ohms. Okay. And let's say the length is 1 meter and the distance or the diameter is 1 millimeter. Okay. So the question asks, what is the material of this wire, right? What is the material? Okay. And we have this table here. So let me get another piece of paper. Okay, so we have our table of values, let's say, and if we get a value that's close, maybe we can assume it's one of these values, right? And so we have our resistance equation, R equals rho L over A. And so it looks like we need to solve for the resistivity to be able to identify which material it is. So that's pretty easy. Rho equals RA over L, okay? This is not so bad. So R is equal to 0.0359. L, oh, that's easy, that's given. What is A again? So A for a circle is pi R squared. Is that right? Okay. What do we have here? R, 2R equals the diameter, so R equals D over 2. Is that right? And so there we have d. Okay, so this area is pi times d over 2 squared. Is that correct? Okay, so this is, and we have to be careful here. Um, I have a millimeter. Is that right? And this is meters. So I have to be in meters, right, for all this to work, right? So this is fine because this is a meter, but this diameter is not just one. I can't just put one, right? I have to convert it to meters. So this is 1 millimeter equals 0.001 meters, right? 1 millimeter equals 0.001 meters, right? So I have to put 0.0359 times pi times 0.001 over 2 squared divided by 1, no problem. Okay, and so the answer I get, do I have a calculator? Let's see here. Let's get the calculator out. Trusty TI-89 that has no batteries. Okay, well, let's get the trusty cell phone out. Okay, calculator here. What do we got? 0.0359 times pi, 3.15, 14159. That's pi, right? Times 0.001 over 2 squared. Okay, so it looks like the resistivity is 2.8 times 10 to the minus 8, and this should be ohm meters. Oh, that's nice. That looks like aluminum. All right. Okay, not too bad. Not too bad. So this would be example. And what I like about this example is it's not just purely the problem. You had to take care of like millimeter to meter conversions. You had to remember your circular formula and all that stuff. But this is an example of, how to put all this stuff together. Okay. All right. And good. Yes, very good. Okay, let's keep moving forward. Okay, so the last physical quantity that we're going to cover today is voltage, right? Voltage is also known as electromotive force. And so here are the four things. Remember, we got the four things: the physical quantity, voltage. This is the easy one. V, 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 right? Um, a bit of trivia, I guess, but it's also important, is that voltage is the same as joule per coulomb. And remember, if you recall, a joule is a unit of energy and a coulomb is a unit of charge. So a volt is energy per charge, right? Remember, charge, what do we think of? Charge is like water, right? So if we have more voltage, we have more energy per that little molecule of water. Does that make sense, right? So it's kind of like a potential, right? You're just building it up, whereas current is like flow, okay? Okay. So voltage is the potential to push current, more energy per charge, and yet more ability to push current. Okay. All right. And just like in current, the like where the arrow direction matters, in voltage, the polarity matters, right? It matters a lot. And so you must have a positive negative. All right. And so here's an example of a circuit element, and you have some voltage, and you have the positive, negative. And like I said, on the street, we say voltage across a circuit element, not through, right? Whereas current, we say through, right? Voltage across, current through, all right? And so here, a very similar example, and you'll see this a lot. There's this dual current and voltage, capacitors, inductors. They kind of behave the same, but like they're backwards. You'll see this a lot, this theme come up a lot in the circuits class, right? And so here you have, let's say 5 volts. Like if I had a red lead and a black lead on a multimeter and I measured positive 5 volts, right? Then it's the same as negative 5 volts, but the positive down here and the negative up there. These are equivalent systems, okay? Not too bad. Okay, let's keep crunching forward. So just like the current, we had a subscript notation. And so if you have two nodes in the circuit element, VAB, the first letter corresponds to the positive node, right? And negative here. So if you had VAB without the positive and negative, you would know to put the positive wherever the first letter is. In this case, A, so it'd be up there. Okay. If you see VBA, you would know to put the positive at B in this case. So that's down here, and then the negative follows. Okay. not too bad. Once you get it, you're like, okay, no problem, right? So the first letter has the positive term, no problem. And again, I like to have a hydro analogy for all these physical quantities. And for voltage, I like to think of it as water pressure, right? Water pressure. And so here's an example. This is a low voltage or low pressure situation, which is going to result in low flow. This is a high pressure or high flow situation, which is going to result in higher flow. So the ability for low or high flow depends on pressure or voltage. Okay, so think of voltage as pressure, right? It's not really doing anything, right? It's pushing, it's pushing, it's pushing. And current is the actual flow, right? Good, 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 good. Some common values. Well, we're all familiar with the car battery, 12 volts. Home appliance, we're all familiar with 120 volts. And I put a little asterisk here because this is actually an AC, all right? And not just AC, but AC RMS, root mean squared. We'll go over that later in this course. Some high voltage power lines, 13 to 250 kV, kilovolts RMS, right? And so high HV for high voltage. And like I said, we'll talk about RMS or root mean square later in this course. Very important stuff, right? Okay. Yes. And finally, we're getting to it. Ohm's law. Ohm's law. This is, as I've said in many classes, this is kind of, I know you guys are in your 20s watching this. Well, maybe if we're on YouTube, maybe some of you are younger or older. But usually on your 20, when you're going to your 21st birthday, I like to say you probably have some parties that you go to. And the next, maybe that night or the next night, yeah. Uh, uh, you might be in a slumber. And what I like to say is, even if I were to wake you up during that slumber and startle you, and I ask you, what is Ohm's law? I want you to be able to have it so ingrained in your brain that you should be able to say V equals plus or minus IR, no hesitation. Okay, this is how fundamental this law is to this class. You have to know this. V equals plus or minus IR. Okay, so this is voltage equals plus or minus the current times the resistance, right? And I got to be careful. You have to be really careful. It describes the voltage and current relationship for resistors only. So it is very tempting for a student to use this law on a voltage supply. No, 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 no. It's tempting to use this for a current supply. No, 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 no. For resistors only. Okay, so make sure that you're applying this law correctly. All right, so let's look at the example where the system is used, right? Or this equation is used. Okay, so there's two versions. You see the positive, negative. Let's look at the positive version. I have a resistor, right? Actually, I didn't even draw the R. I put a little R there. So I have a resistor and I have a voltage and I have a current, right? Now I know there's no numbers. We'll do the numbers next. Let me just show you this first, okay? If I have a V with the positive up here, and notice the current arrow is if this is coming in, right, it's entering the positive terminal, right? Notice this arrow is going to hit the positive terminal before it hits the negative terminal. So that way we say it enters the positive terminal, right? Then we're going to use the positive version, right? Equivalently, you could say it's leaving the negative terminal. That's the same thing, right? Okay, now if I wanted to draw the negative version, I would just draw it the other way with the current going this way. Now, if you flip both, right, if I put the positive, the voltage down here and the current going up, well, you're still going to have the positive version because you kind of did a double negative, right? Okay, all right. And again, I'm just writing it out. Notice the current enters the positive, right? This is what we call the passive sign convention. And you'll see this again with power, right? So this doesn't go away. This is critical. This is critical. All right, getting this correct. Okay. Notice I drew this arrow here just like this. These are exactly the same. This is the same as this. Notice I drew the arrow a little bit ahead. Current is the same with elements in series, right? This is all the same, positive version. Now the negative version, okay, is like this, as I stated, right? Notice I didn't flip both, I just flipped the current arrow. And so the current is hitting the negative terminal first, and we use V equals minus IR, okay? And again, look, if the arrow is drawn here or here or here, but it hits the negative terminal first, we can say that this is leaving the positive terminal and we still use the negative version. Okay. If you're confused, pause the video, just kind of wrap your brain around it, but this is very important. V equals plus or minus IR. These are the two situations. Okay. Okay, let's do a numerical example on this Ohm's law. So I'm going to actually get some paper out and then pretty soon here conclude our lecture. All right, so let's say we have a resistor. And let's say we have 20 volts. I'm measuring 20 volts here across this resistor. And we know that this resistor is 10 ohms, right? The question is, what is I? Right? And so this is like a current sensor, right? If I know the resistance perfectly, and if I know the voltage perfectly, I can actually estimate what the current is. Okay, now we got to be careful, right? I have I here, but I don't have an arrow. So let's put an arrow. Okay, so before we even use this law, again, I want you to build intuition, right? Don't even worry about this law just for 10 seconds. If I measure 20 volts here, I have a high pressure on this side. And remember, this is like a pipe, and I have a low pressure here. Which way do you think current is going to flow? If I have a high pressure here and low pressure here, I think current's going to flow down. Does that make sense? Okay, if I measure high pressure up here, low pressure here, current's going to go flow down. So I would expect that this current value would be a negative number. Okay, so this helps you build intuition even before. Now, this allows you to just blindly follow these rules and get a number, right? And what I'm hoping is that the theory matches your intuition. You always want to be checking that. All right, so let's look at what's going on. We're going to write V equals plus or minus IR. And what I want you to get in the habit of doing is on your tests and your homeworks, I want you to write the law, Ohm's law. Boom, Ohm's law. Okay, V equals plus or minus IR. Now that you've written that out, because you know you're going to be applying Ohm's law, now you can decide if you're going to use the plus or minus version. And I look here and I go, well, am I going to use a positive or negative? And I look at this current and I look at this polarity and I go, well, it looks like this current is hitting the negative terminal first. And because it's hitting the negative terminal first, I think I'm going to use the negative version. Okay. And so this is I enters negative or I leaves positive. These are equivalent. Then I'm going to use the negative. Okay. So that means I'm going to rewrite it. V equals minus IR. And I want to solve for I. So I equals minus D over R. And then I equals minus, now I can just fill in the numbers, a positive 20 over 10, right? That's not to say you couldn't have a negative number here, right? You could have had a negative number here, but we'll deal with that next. Okay, so I equals minus 20 over 10, so I equals minus 2, and we got to put the units, amps. Does this match our intuition? Yes. It's negative current for this situation here. Good. Okay. Let's do another problem. So this one is a little bit more tricky. Let's say again we have a resistor, and let's say we have 15 ohms, and let's say we have a voltage here, but now let's be a little trickier. Minus 35 volts, okay? And we have current going like this. Again, the question is, what is I, right? We have the voltage, we have the resistance, what is I? Okay, Ohm's law. If you just write OL, I'll be happy with that, okay? Ohm's law, V equals plus or minus IR. And in this case, which version is it? Again, I enter, looks like it enters the negative. So it looks like we have I enters the negative, right? So because of this, I entering the negative, we rewrite again, minus IR and solve for I equals minus V over R. Good. Okay, now let's be careful. We can now plug in the values. So we have the minus here, we have the 15 here, but we got to be careful. Now we put the entire minus 35. Do you see that? We have the minus from this, but we have the minus from that. Don't make this mistake of forgetting this minus here. Don't make the mistake of forgetting that minus, right? It's all important. So we have I is equal to positive 35 over 15, which is 2.33 amps. Boom. Okay. Does this intuitively make sense? I should have done that at the beginning of this problem, but let's just see if that intuitively makes sense. So remember what we said, negative 35 with the positive here is the same as positive 35 with the positive here. Is that correct? Yeah, these are equivalent. I did a kind of like a double negative. I flipped this and the polarity. If I have positive 35, it's a similar situation as this guy, right? I have high voltage over here, high pressure over here. I'm going to get positive flow going down. And because of my arrow direction is now pointing down, this will be a positive number. Yay. Intuition confirmed. Okay. That concludes this first ET250 lecture. I hope you enjoyed, and I'll see you all in class. All right. Take care.